Our next speaker this afternoon is Mary O'Gorman, and Mary is a high school science teacher at ACS Hillingdon, and Mary's going to be sharing her work on developing math literacies.
Good afternoon, everybody. Thanks very much for giving me the opportunity to speak today, Ben. I'm really happy to be involved. I've been working through teaching sciences at the high school to grade 9 and 10 students. And we've noticed that between grade 9 and 10, there's quite a leap in the transition from math skills in sciences from middle school through to preparing for IB cycle. So I wanted to look at how I can help the students to perform well in science by enhancing their ability in math within those contexts. When we start out to look at some of the literature available on math in sciences, it can be a little bit overwhelming. There's the negative and the positive side to it, lots of promoting math. Lots of studies that say that math needs to change, how we teach math needs to change in schools, how the Common Core connects with MYP math, and some of the learning objectives for groups like the National Numeracy Association that build on knowledge of kids not having a great understanding of numeracy in their everyday life once they leave high school. Within the UK curricula, this is often because they don't require math at senior level to enter the university programs that they want to take on. That's a little different when we talk about IB, because students generally take math right through, and they have to apply it in more than one subject. However, if their university program they're aiming for doesn't require too much math in the entry level, then they're not going to fix too much priority to retaining that math later. That's not really possible for science, because in order to succeed in the practical aspects of the science courses, students need to be competent and confident in their math connections in the course. The QQC here, or sorry, the OQC, the panel at the very bottom, was something I found very interesting this year, which is a university program that's built into the foundation studies for a variety of degrees that enhance graduates' ability in math for that program. So it applies to social sciences, history, anthropology, all of the regular sciences, and things like English as well, and psychology, where statistics are important in studies later on. So universities are trying to meet this transition gap at the senior level by providing foundational studies at university. I thought maybe we could do something similar to help the students transition from middle to high school on a more condensed level. The question that I asked was, how can teaching strategies that build 9th and 10th graders' data collection, analysis, interpretation, and evaluation skills contribute to the science learning outcome? The focus of the study was to look at what I can do as a teacher to make learning easier for my students, so that they learn how to collect data appropriately, they understand how to build connections with their data and their task, and they can accurately evaluate what that means in a math-based context. With a stepwise introduction, this should build from some surveys and questionnaires through to the students applying those skills in their inquiry and practical focus across the sciences, and then become confident and be able to contribute their learning within the school community and outside of it, and see how it can contribute to the wider global citizenship initiative. Ultimately, this also makes happy teachers, so you'll see the Apple icon wherever you see that later. The first objective in the study was to look at how teacher-led instruction in either the investigation or the reporting phase of a practical piece of science work might help the students improve their ability. To put this into context, I focused on the quantitative skills that students would need in a physics example and a biology example of a piece of practical work. I wanted to focus on how the students were collecting their data with the bigger picture of the study in mind, whether or not they understood the calculations required to process their outcome, and then could they process that information by communicating their interpretation and their understanding of the result. If this was successful, what I would look for was their ability to analyze, interpret, and evaluate their own outcome for the task. So the first example allowed students to independently investigate and then receive guidance on how they reported. So this was a mixture of grade 9 and 10 students, varied learning abilities, studying light. The task that they were given was to study refraction, or Snell's law. They had to make an association between two different angles and use a formula that would connect those angles and prove that the formula was always equal at the beginning and at the end. This is an example of some of the variation that I received from students in their reporting. You can see some students like to use a lot of color in their tables, but perhaps don't see how easy or difficult that is for a teacher to access in terms of grading. They spend a lot of time on the design, but don't necessarily think too much about the numbers. You can see these decimals have maybe 8 or 10 places in them, so the student isn't sure how to narrow it down. In the second table at the bottom, it's a little clearer, black and white, easy to read. The decimals are rounded for the most part, but there's no units put into the table. So while we know it's an angle measurement, the student hasn't designated whether they're measuring degrees or something different. With graphs, we saw a little bit of variation in how students present the data, whether there's a trend line, a connector line, and then whether they can process the analyzed data in the bottom graph where the angles are associated. With this level of the task, the reporting had some guidance. So to do this, I put on the main classroom screen a Google Sheets. We took a class set of data. I worked through it stepwise. The students pretty much copied what I did, jotted down their process, and the intention was that they would repeat that in their next lab. Unfortunately, that didn't happen. Though they were able to really discuss what they did because they had time to investigate, use equipment, talk with each other, ask me questions, try things out and see what worked and what didn't. They were extremely fluent in describing the experiment, describing how they went about it, and telling us what result they got. They could describe it in their own language, in their own context. But when it came to looking at this data and explaining the data to me in a scientific language, that was really, really difficult for them to do. We still had descriptions like when one goes up, the other goes down. The graph makes a straight line. What does that mean? I don't know. It makes a straight line. It looks right, so it's okay. So it highlighted for me those math literacies in data processing are easy for them to understand as they're doing it, but how do we get them to retain the practice? To take that an extra step, I thought we could create some task cards using Google Sheets or using Excel that students have to make reference to every time they want to do the same idea. The students themselves are working on building this because some of them use the program in other subjects, so they're learning how to adapt it for science. The second study example was where the investigation was guided, but the students were allowed to report it in whatever way they thought was best. So to guide the investigation for biology, students were asked to allow a piece of snack food to burn in the lab. The heat created by the burning heated up some water. They measured a change in temperature to the water and then worked backwards to say how much of the food burned up for that temperature to change. By measuring the difference, they were able to use a math formula to find out how much energy was in the food content, because the energy in the food transferred to heat energy in the water. So in guiding students through this, we set up a piece of equipment in the lab. We worked through it step by step. Students were able to get the concept that the burning food heated the water, and they understood there was a formula to use later, and it was relative to temperature and mass and various other science measurements. What they weren't totally solid on was how to put this into tables and graphs. And as you can see, these are three different ways that students over a class of 25 individuals balanced out what they did. The graph in blue is an example of a student who graphed the temperature change. When the temperature change was graphed, the student was able to derive what that meant in terms of the heat from the piece of snack food. As the heat transferred the water, everything increased. So this evaluation and discussion was about temperature increasing with little attention given to calculating the energy. The second graph is much closer to the mark. The student measured the change in mass between the snack food before and after burning, because this student recognized that the mass was relevant to calculating the energy. And this student was able to put that into the calculations for energy in a table, but didn't think they needed to graph the energy relative to the temperature, or wasn't sure how to graph the energy relative to the temperature. So this shows the general groupings that happened within this task. What I got from this was that students know how to plot graphs. They know how to plot tables. And where they need to, they can put it in the right orientation. But even with a guided experimental run-through and several discussions of how to use a formula for a derived answer, students still find it difficult to put the correct data or the best data into the report to tell us what their experiment means. To try to address both of these within this study, I asked that given the variation in students' understanding of how they manage the tasks, how can I put something into my teaching strategy that modifies or supports them in becoming more independent? How can they make those connections that they seem to be missing? To do this, I took the assessment rubric that I've been using and I built it into chunks in a checklist-style piece of work. So every student was able to self-assess their most recent piece of lab work according to these checklists. The checklists account for their inquiry, which is the one on the left, and data collection and analysis, which is the one on the right. And they run two separate types of assessment. So by using these checklists, students could see where they met the task requirements and where they didn't. Interestingly, with the biology task, in criterion B, the green line, which shows the grades I gave the students, pretty much matches the grades the students gave themselves, which shows me that they understand really well what's required when they have to plan an investigation. And that includes setting out the math they have to use to get the result. So I was happy that they understood this, and doing a little bit of statistics on it, they relate very well. So I'm happy that students know how to plan it. But when we talk about reporting the data, collecting the data, analyzing the data, presenting the data, you can see a lot more variation, particularly among the students who scored grades between a 1 and a 3, which would technically be my lower ability group of learners. So within this group, these students have a wide variety of their interpretation of what's required for the task. Some of them miss the point of the math completely. Others know they have to do some math, but they're not quite sure how far they have to go. And then there are some that no matter how many ways we've described it, they're still unsure how to present the math in the work. You can see from the statistic bit as well that, this is significant within this group. But again, this is a group of 25 students, and the study would be much stronger on a much wider scale. It's indicative and it's interesting. So looking back to the original question, overall, what I found was that students retain a strong ability to qualitatively assess their work and their individual findings. They can investigate, they know how to make assessments, they know how to collect evidence and analyze discrete data, simple data, simply and effectively. Where they fall short of the grading mark, where their math abilities are challenging for them, is in making plans to account for replicates in their study. If they only have one result, they don't see the need to make a calculation where someone told them they had to have an average, because they only calculated one thing, so why would they need an average? They'd forgotten they have to plan to collect data so they can get an average. Identifying and using the correct math formula for derived measurements. A lot of students find this challenging, especially if there's more than one step to the formula. Selecting and presenting the most appropriate graph can also be difficult. A lot of students just base it by eye. Does it look right? Is it telling the story that's in the table? If it is, then that's the one I'll use. But it may not be the one that's best for their story. So step-by-step teacher-led guidance and resource supports don't really seem to be enough in this group for students to retain and apply their active learning outcomes when they have to quantify something. At the moment, I'm taking this just a little bit step forward with my students in that I'm sending out some questionnaires. I'm continuing with the process to try and identify which parts of the report they give priority to and whether their priority matches the assessment priority. Their main concern, obviously, is achievement. They don't want to have low grades with this, but within a stringent set of assessments, they're stuck if they can't overcome this. So my role in the research is to help them overcome it also. In the whole process of this and investigating methods for incorporating math, I've also been heading up a STEAM program in the high school this year. It's an elective class, so students who are interested in applied sciences want to take this on. STEAM generally can be considered, in a way, a model for math integrative teaching strategies in science, because the math skills are the ones that connect all of the other aspects to the program. STEAM could be characterized by all of these different things and a huge amount more. But the key thing about it is it connects the areas of science, technology, engineering, arts and communications, and math. And math really is the hinge to it. Once students are confident in how to put numbers together, they can create projects and they can be very dynamic in what they do. Within the space of a couple of weeks, my STEAM class were able to build the skills they needed to model an aircraft, to test it for best distance and trajectory and height by making paper airplanes and by making more robust models of rockets. They've been able to get the skills to put electronics together and code for measuring distance using a small ultrasound attachment to an electronics configuration. They're now learning the code to build an altimeter so they can attach it to the rocket and measure in real time how high that rocket can go with an optimum wing design, lightweight materials, and everything they've learned overcomes the forces that prevent something from taking flight. So they've touched on physics, technologies and electronics, engineering and materials. They're going to use arts and communication to create role plays for people in an industry that might build this model. And they've put all of their math thinking into play to get it to work in terms of scale, three-dimensional design, graphic design, to make a really, really nice project. All in the space of a few weeks without a set of robust criteria to tell them what they had to do. It wasn't prescriptive. Extremely enlightening when it takes such a level of process to understand how students in single-streamed sciences are struggling just to put a formula into action. So overall, as an entire summary, it's really challenged me to ask, what is it that students really want or need to improve how they apply math? Essentially, they need to have the same qualities in applying math that make them want to go out and code something or build something. They need to have the same desire that they have to get out of class early for a football game, or to go to a concert, or to run through an audition. It needs to drive them in the same way. And the only way that I can see to make that possible is to make their math context in science really tangible to their frame of reference. Where students want to invent, they need to be given opportunities to investigate. Where they really want to ask questions, they need to have access to appropriate literature, good scientific literature, news and media. Where they want to develop new skills, they must have the parallel toolkits, the time to learn, and the purpose to show those skills in action. Where they want to feel accomplished, they need to have alternative access to math complexities so they can see what it is at their level before they have to tell it like a scientist. And where they want to win, where they want to really achieve those grades, they must have a purposeful structure and a tangible application to what they're learning. I feel that STEAM as a model program can show us a lot about how to parallel our math curricula with our science curricula for the best benefit of the students. Currently, that's not always the case, and there are challenges in every subject that we teach that aren't always put together. But I feel that in trying to really enhance students' math abilities in sciences, we must collaborate as separate teams and as collective teams to put the skills, the formulae, the tools, and the practice in at the same time. As Ben said at the beginning, this really is a work in progress. There's a lot within this area that's changing, and curricula are changing in math particularly, and in sciences all over the place. So it's very difficult to tie any strategy down. I'm really grateful to have had the chance to look through this with my students. I feel they've enjoyed the creative side of the process. There's been some consternation where they've not seen a parallel between what they thought they should be getting and what they are getting. But again, that puts us in a very strong position that now they've experienced the difference. They understand what it feels like, and they really want to know how to manage it better. So to finish, I'd just like to say thank you very much for all of your input, for all of the help that I've had and support that I've had through doing the project, and for any feedback that you might be able to give me later on. Thank you.